All right, let's talk about residual current devices, or RCDs. They're one of the most critical, but maybe one of the most misunderstood life-saving parts of any modern electrical installation. Think of them as the silent guardians in our circuits. So let's dive into why these little devices are absolutely non-negotiable for both safety and for compliance.
To really get why this is so important, we have to start with the risk. Check this out. Data from the Institute for Damage Prevention and Damage Research shows a pretty staggering 31% of all fires are caused by electricity. Now, that's not just a number on a page. It's a huge and, more importantly, a preventable hazard in our homes, our offices, and our factories.
And the danger isn't just about fire. The international standard IEC 60479-1, which spells out exactly what current does to the human body, is crystal clear. The moment a current flowing through you gets above 30 milliamps, it can stop you from breathing and, most critically, cause ventricular fibrillation. That right there, that's the lethal line in the sand that shapes our entire approach to keeping people safe.
So how do we actually defend ourselves against these invisible dangers? Well, the answer is in this brilliantly simple principle of physics, all wrapped up in the residual current device. Okay, so here's the core idea. An RCD is a safety switch built to do one thing and do it incredibly well. It spots an imbalance in the electrical current. It's so important to get this. It's not looking for overloads or big short circuits. That's a job for a circuit breaker or a fuse. No, an RCD is looking for a leak.
So a healthy circuit is all about balance. The best way to think about it is like a perfectly balanced scale. The amount of current going out to your appliance on the active wire should be exactly the same as the amount of current coming back on the neutral wire. When the supply equals the return, everything is good. The system is safe.
But what happens when something goes wrong? Say the insulation on a wire fails. Or worse, a person touches a live part. Well, some of that current finds a new way to get to the earth. It literally leaks out of the circuit. And that leaked current, it could be flowing right through your body. The scale is now unbalanced. More current is going out than is coming back in.
And this is the RCD's heroic moment. It is constantly watching that balance. The second it senses even a tiny difference, that residual current, we're talking as low as 30 milliamps, it trips. It just slams the power off in milliseconds, way faster than a human could ever react, and long before lethal shock can do any real harm. Now that principle is just beautiful, and it has saved so many lives. But here's the thing. The electrical world has changed. The kind of devices we use every day are creating new, hidden dangers, and frankly, the older RCDs just can't keep up.
Okay, pay close attention, because this table is absolutely essential for any electrical designer today. A classic type AC RCD was built for simple old-school loads, so it can only detect those clean sinusoidal AC fault currents. But our modern electronics, they've completely changed the game. Power supplies in our computers and TVs create pulsating DC fault currents. Variable speed drives, they can spit out mixed high-frequency faults. And things like solar inverters or EV chargers can produce smooth DC fault currents. A Type AC RCD is completely blind to all of that, which means it just won't trip when it's supposed to. And that is why we have Type A, Type F, and Type B RCDs. Each one is engineered to see a wider, more complex range of these modern fault types.
So, the takeaway here is huge. Picking the wrong type of RCD isn't some small mistake. It's a massive safety failure. As the standards like AS/NZS 3000 keep evolving, the message is loud and clear. You can't just slap a Type A CRCD on a circuit that has modern electronics anymore. It's just not acceptable. Type A is really the new minimum, and for the heavy hitters like VSDs or PV systems, you're often required to use a Type B.
But the RCD isn't an island. It doesn't work all by itself. To choose the right one, you first have to understand the very foundation of the building's electrical system, its earthing system.
All right, so the IEC 6064 standard lays out three main systems you're going to come across. You've got the TT system, where the supply and the building have their own separate connections to Earth. Then there's the TN system, where they share a common Earth connection. And finally, the IT system, which we'll usually see in critical places like hospitals, where the supply is actually kept separate from the Earth on purpose. So why does all that matter? Well, because the type of earthing system completely changes what the RCD's job is. In a TT system, the path to Earth has a lot of resistance, so the fault current is often too weak to trip a normal circuit breaker. In this case, the RCD is the primary protection. It's not optional, it's essential. In a TN system, the fault currents are huge and will trip a breaker, so the RCD acts as a vital supplementary protection. an extra layer of safety. And in an IT system, the RCD is used selectively, only to clear a fault after a second fault happens, to keep everything running.
So this brings us to what this all means for you, to your professional responsibility as an engineer or an installer. Getting this right isn't just about checking a box on a form. It's about the fundamental duty to protect people's lives and their property.
Let's just boil this all down to 4 rules you cannot afford to ignore. Number 1, RCDs save lives, but only if you pick the right one for the job. Number 2, our modern world of electronics demands modern RCDs. You have to be thinking Type A, F, or B. Number 3, you simply cannot choose an RCD until you know the building's earthing system. It sets the entire game plan. And finally, number 4, if you are ever in doubt, the standards and the manufacturer's data are your ultimate source of truth.
And that really leaves us with one final thought. The electrical world is changing faster than ever. The things we're plugging in today are just worlds apart from what we were using a decade ago. So the real question isn't just, is my design compliant today? It's, is my design philosophy truly ready for the electronic world of tomorrow?